Okay, so welcome to my second in my series on gradients and areas. So this video is designed to follow on from the previous one where I looked at gradients and areas in the context of mechanics and materials. So a lot of the skills I'll be using in this you will come across in that video, so if you haven't had a look, do check that out. But essentially what we're going to be looking at is how we can calculate various properties from the different graphs you come across in electricity. And by properties in terms of electricity I mean things like current, potential difference, resistance, all of those kind of very common things. So all you'll need to do this, your equation sheet, and be able to rearrange some equations to y equals mx plus c form. You can do that, let's get cracking. Okay, so right at the start of electricity you'll come across these. They're called IV curves, IV graphs, that kind of, or characteristic curves, those kind of things. And what you have is current plotted against the potential difference. So to be more specific, this is the current going through a component and the potential difference across that component there. So from your formula sheet, you'll be familiar with this equation here, and we want it in y equals mx plus c form for this graph. So we need to make I the subject, so that's what we've done here. So what you can see from this is that the gradient of this graph is 1 over the resistance. So it gives us an idea of what the resistance of the component is from the graph here. So that's the first one we want to look at. Another graph we can look at is about the resistivity equation here. So in this instance I've decided to have a graph of resistance against the length of a conductor. So what should be quite intuitive in your head is if you have a longer conductor, that's going to have a bigger resistance. Okay? And that's definitely true. So the equation linking resistance and length would be this one here, where your resistance is resistivity times length divided by area. So I'm going to juggle that around slightly so we can see the y equals mx plus c form. So I've just essentially taken the L out of the fraction. So you can see that the gradient of this graph would be resistivity divided by the cross-sectional area of your conductor. So in order to find resistivity, which is what you might want to do, what you need to do is work out what the area of your conductor is. And typically you'd use something like a micrometer to measure the diameter and calculate your area from that. So that's your general approach there. Okay, so the last key graph you'll come across with the DC circuitry stuff is the EMF, well, the graph to calculate EMF, and it's actually a terminal voltage versus current graph here. Now, one thing you might spot straight away is that although generally speaking this looks like the graph is of the right form, there's quite a big problem with this graph, and it's something that comes up quite a lot with this. So let's have a look at what that is. So you'll see this equation in your formula sheet. EMF is terminal voltage plus the potential difference across your internal resistance. Okay, so if we rearrange that, you've got terminal voltage on your y-axis, we're going to get this form right here. So you've got your potential difference across your internal resistance and your EMF. So we've introduced a plus C term for the first time. Now what a lot of people miss out here is they see this one here. So we've got minus the internal resistance. So actually the graph wouldn't look like this at all. What the graph looks like is something a bit like this. So it should be a straight line with a negative gradient there, because the gradient is equal to minus the internal resistance there, and the internal resistance should be a positive value. So actually your graph should look like the green line I've drawn in there, not the original line of your graph. Right, so now let's go on to something a bit more interesting than those basics from the DC circuitry. Some of you might be wondering, well, what's represented by the area under an IV graph, for instance? Which is a great question to ask. So the key thing is, when finding an area, what you're doing is you're integrating. And what you actually integrate is the equation of your line with respect to whatever's on the x-axis. So we know from earlier, the equation of this line is I equals V over R, or 1 over R times V as we had it earlier. That's the equation of our line. And our potential difference is on our x-axis, so that's what we're going to integrate with respect to. And what we're trying to find out is what's essentially represented by the area between two potential differences that we're integrating between, so the area between these lines here. So resistance is going to be a constant, so we can kind of factor that out. And V, when you integrate, becomes half V squared. So that's why your 2 has appeared in there. So what we can do is then plug in I equals V over R. So that's why we've gone from V squared to some like current terms in there. So that's where that's come from. And if you look at your formula sheet again, you'll know that IV is a power calculation. So it calculates the power at this current and this potential difference there. So the area between this point here actually represents the change in power, but divided by 2. So if we want to know the change in the power dissipated between this point here and this point here, what we need to do is work out what the area is and multiply it by 2. And that's what is represented by the area under your graph in this instance here. So fairly interesting. Now even a bit more interesting, using some calculus, is there's a scenario, say, I don't know, you're trying to use an electric heater, for instance. And you want your electric heater to dispense as much thermal energy or power as possible, because you want to essentially heat something up as fast as you can. So you need to design your electric heater circuit in such a way to maximize the power from your resistance. So what we're going to have a look at doing is how we can calculate what the value of the resistance of our heater should be in order to maximize its power. So we've got a general circuit here. We've got a power source, we've got some internal resistance for the power source, and then we've got our electric heater, which will be a resistor, because obviously resistors transfer electrical energy to thermal energy, so they're heaters. Okay, so first of all, let's use a potential divider equation. So if we want to know what the potential difference is across R, we essentially use a potential divider equation to work it out in terms of the EMF and the resistances. Now, from your formula sheet, you should know that power is V squared over R. So if we square RV and divide it by R, we end up with these expressions here. Now, if we want to find the maximum power, that's telling us we're going to do some differentiation. When you're trying to find a maximum, we're going to do some differentiation. And we want to find the resistance we get maximum power, so we're going to take the derivative with respect to R. So that's what you can see happening here. Those of you who are wondering what on earth is going on here, I'm just using the product rule, which you'll learn about as part of the A-level maths course. So essentially, I've split this term up here into R times 1 over R plus R squared. So I've split it into 2 parts, and I'm using the product rule on those 2 parts. And then you can work through and do some cancelling out, because we're equating it to 0, because we want the maximum. And we end up with this really nice expression at the end that your internal resistance and your external resistance should be equal to each other to transfer the maximum power to your external resistor, and therefore dispense the most thermal energy per second if you're trying to heat something up. Okay, so I hope you found that quite interesting. I certainly enjoyed having a go through that. That's good stuff. If you notice any problems, as per usual, or you've got any questions about this, please do post them as comments. But as always, thank you very much for watching.